get started here briefly, or in a brief moment. I'm sure some more people will trickle in, but that's all right. They'll catch up. So today, yes, I'm muted. I'm gonna start talking to you. Okay. Yeah, we'll get started here. So yesterday I sent an email that had in it or attached some kind of practice problems relating to the material here from Chapter 5. It's also, I think, posted under Chapter 5 on the Canvas, so you can find it there as well if you want to look at it. So hopefully you had a chance to at least open it up, kind of read through, think about some of the questions. My guess is you'll get a little bit more out of it that way, but even if not, we'll walk through some of those today, and it'll, hopefully my goal is that it opens up kind of not only how we approach some of these, but some of the questions we might be able to answer with these types of methods. Okay, so we will jump in and just grabbing a marker. So yeah, I think these will give us a good kind of starting place as far as building on these concepts. Let's see. Try to find some good markers. All right, so the first question is one involving LeBron James. Okay, so we're imagining a scenario where LeBron is fouled on the final buzzer beater and he misses it, but now he's got 2 free throws and they're down 1, so no time left on the clock. So we are probably concerned about, okay, so LeBron has 2 shots. We want to know the likelihood of him winning the game in these shots or him losing the game. We also know that LeBron is, so the probability of making a free throw for LeBron is 0.74. Okay, and we know that from empirical evidence. So we've seen LeBron shoot thousands of free throws, and he has made in the past 74% of these, and so it's a pretty good assumption that he has a 74% chance of making any free throw that he attempts. The other thing we're going to assume is that, so he has 2 shots. We're going to assume that these are independent. Okay, and so the probability of making the first, I'll indicate that as M1, is 0.74. And the probability of making the second is also 0.74. Okay, and this is an important assumption. And so what we're saying here is that if he misses the first, it doesn't tell us anything else about whether or not he'll make or miss the second. You could quibble with this maybe a little bit, although the evidence, the empirical evidence for basketball and pretty much any skill-based sport is that they largely are independent. So even though we have the sense of players getting hot or cold during a game, when you crunch the numbers, it actually ends up that those are just kind of randomness built in. And you know, if you miss the first penalty kick of the game, it probably doesn't change, or empirically doesn't change your likelihood of missing the second one. So we have independence. And when we have independence, that means that we don't have to worry about any conditional probabilities, and the probability of him, so if we're worried about winning the game, how do we win the game in this scenario? We need to make the first and make the second. Okay, so for LeBron to win, he needs to make both. And so what's the probability that he makes one and makes two, or the second? Well, in the independence case, That's simply the probability of M1 times the probability of M2. Okay, so we can just plug in 0.74 times 0.74, and we end up with 0.548. Okay, so a 54.8 or 55% chance that LeBron wins the game directly in these two free throws. Okay, we also are concerned, how likely are we to end up with a loss? Win and lose makes more sense. Or win and loss, I guess. Okay, so what is the chance of a loss? Well, we need to think about, so they're down 1. So if he misses both, they lose. Okay, so how do we figure out the probability of missing? Well, he's going to take a free throw. Okay, so he has a chance of making the free throw. The complement of that is not making it, right? We're assuming there's only those two options. I don't know what happens if the ball gets stuck on the rim, but basically there's only the two things. So anything that happens that isn't making it is not making it, right? Squiggle making it. And so to lose, we would need not make 1 and not make 2. So what is the probability of not making 1 and not making 2? Well, it's simply, again, we have independence, so this is the probability of not making 1 and the probability of not making 2, or multiplying those together. I guess we didn't fully calculate this, but if the probability of making is 0.74, then the complement is 1 minus 0.74, or 0.26. Okay, so we have a 26% chance of missing. So when we think about missing both, we can plug in 0.26 times 0.26. We end up with, what does that become? 0.068, or a 6.8% chance that he misses both and they lose the game. Now, there's obviously other things that could occur, right? So he could make one of the two and end up in a tie. Okay, so we could go through the math, and maybe we will here in a moment. We could tie. Okay, but we could probably short circuit that and not have to plug in all the numbers if we just think again about the world of the complement. Right, so let me redraw. I think I can fit it in here. So in terms of winning, losing, we have another Venn diagram where we either win, we lose, or everything else is a tie, right? And in this case, that includes making and then missing, or missing and then making. But here we already know this is 54.8%, this is 6.8%, and so everything else has to equal 100%, or everything else equals the rest of the 100%. So we can figure out the likelihood of a tie by simply saying 1 minus 0.548 minus 0.068, and that's like with some rounding, that's going to give us 38.4%. Right. Okay, so 38.4% chance that we tie and we go to overtime. Mathematically, or using our formulas, what are we talking about in terms of chances of a tie? So we could, what's the probability of making the first plus missing, so not making the second? Or, of course, we could do probability of missing the first, and then he makes the second. Okay, again, these are independent. And so this is just going to be what? Making the first is 0.74 times 0.26. This would be 0.26 times 0.74. Both of these, I think it's 0.1924 or something. Okay, and then as you see, if we add both of those up, right, because both of those are tying, that would be, what, 19% and 19% gets us about to the 38% that we were talking about. Okay, so when we have independence, the equation is pretty straightforward, right? We're really functioning with this type of mentality where we can just multiply those probabilities together. Now, again, that's a big assumption to say, and I don't think we're wrong here, but we are making that assumption that the probability of the first and the probability of the second are independent of each other, and that whatever happened in the first shot doesn't change the second. And maybe you would, I don't know, maybe the pressure is a lot higher, and so we would maybe quibble with this a little bit, although I do think the evidence kind of still supports this. But now, this independence is not always going to be true. So what we're going to turn to next is an example where we can't make that assumption. And in fact, we can logic our way to knowing that that is completely not true. So we're going to imagine, and I think this is problem 2 in that sheet that I sent out, we are considering a bag of marbles. Okay, and I think on the sheet I have listed blue and green, but I don't have a functioning green marker here. So we are going to talk about blue and red marbles. And we have 3 of each color in this bag. Okay, and we can see them here, but imagine that we can't see them. We have to put our hand in, mix it around, pull a marble out. What we're curious about is what are the odds that we pull out a red marble and then another red marble. Okay, so we 2 times in a row pull out a red marble. And so to look at this, we're going to look at we're going to build this with classical probability, right? So there's these multiple ways to develop the probabilities. With the LeBron example, we looked at we drew from empirical results, right? We knew how many shots he had made in the past. Here, we're able to mathematically build the probabilities. So what is the probability that that R of R1, so the first marble being red? Well, we have 6 marbles, 3 of them are red, and so if we take one randomly out, that's going to be 3/6 or 1/2. So I'm going to just write down some more probabilities. We won't need all of these for this calculation. But the probability of blue on the first is also 1/2. Right? And just to clarify what we're after, we want, what is the probability of R1 and R2? Okay? So similar in the sense of we were curious about LeBron making both, right? Making 1, making 2. Here we want red 1, red 2. But as we'll talk about, the math is a little bit different. And it's different because when we turn to the second marble, we need to update a little bit. Okay, so right now, before we do anything with the first marble, if I ask you what's the probability that the second marble is red, we can answer that. And in fact, the probability of R being R2 right now is 1/2. Right? Because we don't know what's happened in the first marble. And the probability of blue 2 is also 1/2. But we're not going to use these 2 probabilities in our calculation because these are states of the world where we don't know what happened in the first marble. What we are after is the case where the first marble is red and the second marble is red. So when we get to that second marble, we're interested in the state of the world where the first marble was red. So what happens to our probabilities when the first marble is red? So what's the probability of the second marble being red if, or given that the first one was red? Because if it's not red, we don't really actually care about it in our end calculation. So in the case that we drew a red marble out, okay, we took a red marble, it's outside of the bag, now we go back and put our hand in the bag, the probability of drawing a red marble has changed. Okay, it's conditional, it's a conditional probability. It's no longer just simply red 2, it's red 2 given that there was a red 1. Okay, and we can again calculate this percentage, or this likelihood, because we know, well, now there's 5 marbles, 2 of which are red. So it simply is 2/5. Ooh. 2/5. Okay, we can calculate more of these conditional probabilities. This is the one that we're going to use, but we would also know what the probability of red 2 given blue 1. Right? So imagine instead of the red coming out, we had taken a blue, now we'd have a 3/5 chance. Okay? Let me put that back. So now we're ready to put together our equation. In the previous example, when we had independence, we were able to use what's called the special rule of multiplication. And that was, so I'm just going to rewrite it up here. So we did probability M1 plus M2 was simply the probability of M1 times the probability of M2. Okay, this was the LeBron. That is only functional when this is independence. If we don't have independence, we can't use this special, that's the special part of it, that it is independent. We don't have that, we have to use the general form. Okay, and so in our case, the probability of R1 and R2 is the probability of R1 times the probability of R2 given that we had R1. Okay, so the probability of R1 times the probability of R2 given R1. And that's because we have to update what this probability of R2 is for this state of the world. Okay, so this becomes 1/2 times 2/5. Okay, if we were using the specific or the special form, right? So this is the special. I think that's the way the book refers to it, and this is the general. If we accidentally use the special form, we would simply do 1/2 times 1/2, and we'd get a 25% chance. Here we do 1/2 times 1/5. What is that? 2/10 or 20%. Okay, so going into this, we now know that if we want to grab a red and then another red, we're going to do that 20% of the time. So you can see that's different than if we use the wrong calculation, we get 25%, 5% difference, not a huge deal, unless somebody gives you a gamble and says, I'll pay you $4 if you get it, and it costs you $1, you're going to come out behind if you're using the wrong, or if you're you're going to come up behind, and you might think it's okay if you use the wrong formula. Okay, so one thing to note is the general formula can be used anytime. Okay, so let's just think about the LeBron situation. We couldn't, so here we used, this was what, 0.74 times 0.74. Okay, we could write it in the general sense. We could say, what's the probability of M1, and then the probability of M2 given M1. We can write it that way because we know, we were assuming that there is no update, and so this is still 0.74. Okay, it doesn't change based on M1, so M2 is just 0.74 even with the conditional. So you can always use, this is the general down here, so you can always use the general, and this is true for the multiplication and for the addition equations that we come across in Chapter 5. We can always use the general, it's just the special is sometimes easier or quicker in some sense. Okay, so that's a conditional probability. And again, that's one of the things we're going to have to keep track of as we do these probability kind of questions is to really take the time to think about what's the specific scenario that I'm concerned about, and can I defend things like independence? Or do I need to worry about the conditional probabilities? So the next question, question 3, we're talking about the Twins. Okay, and I think I mentioned that they are losing, or they lost the first game of the playoffs. They're in a best-of-3 series. They lost to the Astros yesterday. And so we might be curious, what's the chance that the Twins survive the series and win the series? Okay, so they're down 0-1. They need to win the next 2 games. Now, here, I'm making a subjective probability. Right? I don't have a classical way to build this probability. I don't have an empirical. You could maybe rely on, maybe the Twins played the Astros a certain amount of times over the last few years. You might be able to rely a little bit on that, but largely we need to take a little more subjectivity into this. And so what I'm going to say, the Twins, I'm going to give them a 45% chance to win each game. Okay, and so a little bit about that, that means that we must be considering this as independent. Right? If I simply just give them a 45% chance to win each, that's not saying, okay, it's a, they got a 40%, and then if they win, it's a 60% or something like that. It's just 45% each time. So we are back to independence. And so if we do care about them winning, they need to go 2-0. And so they need to, what's the probability of win 1 and win 2? Or win the first game and win the second game? Well, independence means we can just jump to the special rule. Probability of win 1, probability of win 2. Again, we could think of the general rule, right? All that changes in the general rule is that we make this a given that they win in the first, but since we have independence, that's the same thing. It doesn't matter if we put that in there. So this simply becomes 0.45 times 0.45. Okay, and that is 0.2025, or about 20%. So if you think that the Twins have about a 45% chance of beating the Astros in any game, which again is a little subjective, and if you think the Astros aren't cheating this year, maybe the Twins have a better chance, but who knows? then you would think that they have about a 20% chance to come back and win the series. So don't get too excited. They're probably not going to continue. And maybe you're used to that, because as the second part of that question 3 indicates, is that the Twins are also a record-breaking team. Okay, so yesterday's loss to the Astros also was the 17th straight playoff loss for the Twins, which is a record for not just baseball but any sport or any major professional sport. But probably anywhere. And so we might be curious about how unlikely this is, or what's the likelihood that the Twins would do that. And we're going to calculate that. So I have listed here in this question that maybe they were big underdogs and they lost, or they had a win probability of 30%. I'm going to change that to 40%. So let's say across all these 17 games, they had a win percentage of, or a likelihood of 0.4. The probability of a win equals 0.4. Now, if we wanted to be really specific about it, we might, we just said they had a 45% chance against Houston, and maybe they had a 40% against the Yankees and the other teams. We could break this up. But let's say for all of them, they're 0.4. So what's the likelihood that they lost all of these? Well, we're going to rely on a couple things. First, this is a chance for a win. We're interested in losses, and again, relying upon the fact that you're either going to win or not win, right, or a loss. Especially here, we're in the playoffs. There's not going to be any ties. We know that the probability of not win is 0.6, right, or the probability of a loss. Now, we need that to happen more than once. So just like up above, we can start to multiply these. Okay, so the probability of losing 2 in a row, I'm just going to put PL. PL1 times PL2. Now this formula can continue. So we can continue to multiply on. So probability of win 1 plus win 2 is multiplying them together. If we add another one, we just multiply again. So this is a more flexible form than just 2 items. So we can keep adding probability of L3 and so on, all the way to probability of L17. Now, because we are assuming that they're all the same probabilities, we can shorthand that and say, what are these? These are 0.6. So it would be 0.6 times 0.6 all the way to 0.6, right? Again, shorthanding that. What we were really after is 0.6 to the 17th power, right? What we did up here was 0.45 squared. Okay, this time we want to lose 17 in a row, so we're going to raise that to the 17th power. And what is that going to be? So 0.6 to the 17th, I get, and you can double check this, but 0.000169, or what is that? That's 0.017%. We'll just round it there. Okay, so less than 0.02%, an absurdly low likelihood that that would occur. So maybe that makes you feel better just because it's exciting, right? So you're seeing something that is extremely unlikely. So they probably weren't going to win anyway, so it's at least exciting that they lost in such a fantastic fashion. So you take your positives however you can find them. Okay, so next we're going to switch gears a little bit, and we're going to talk about a tool that we use quite often, And one thing, and it's a tool that we saw last chapter in chapter 4. That is the contingency table or the pivot table in Excel. So we often display our data in this tool because it, as we'll see, we can keep all of the data we might need in one nice little area and be ready to quickly find it. Okay, so I'm going to put up, this is the Titanic data. So I don't know if you made this exact pivot table, but you probably made one very similar. So we had data on whether or not people died or survived. Okay, and we knew that 809 died and 500 survived for a total of 1,309 passengers, right? And so we have our frequency table. And again, that contingency table is just basically two frequency tables smushed together. So we have first, second, and third class. And so that frequency table, there were 323 first, 277 in the second class, and 709 third class passengers. Okay, again, totaling to that 1,309. And then the big benefit of the contingency table is that we have this middle part here where we can know that there were 123 first class passengers that died, and so on. 200 of them survived. Second class, 158 and 119. And then 528 third class died, while only 181 survived. Okay, so we have a lot of data or a lot of information packed into this one chart. And so we can answer a lot of questions directly from this information. And in fact, I'm forcing you to do that in some of your assignments because it is a good way to kind of wrap our heads around what we mean by various probabilities. So we can start basic and say, okay, what's the probability that someone survived? Okay, a random person, or imagine you're just one of the passengers and we don't know the class, right? We're at this point, we're not asking anything about the class. So we're just, in total, across all the passengers, what's the likelihood that an individual passenger would have survived? So here we're relying upon the empirical results, right? So we have the data. And so survived, we know that 500 survived out of 1,309. So we have 500, 1,309. And I did write that down. Something like 38%, 0.382. Okay, so 38%. So just going into it without knowing anything about the class, we know 38%. Then I think I do ask, what if they were a third class passenger? Okay, so what's the probability that you survived, or the random person survived, given, right? So we know now that they're a third class passenger, so given third. Okay, so we're into conditional probabilities, just like we had with the marbles in the bag. We have more information, so we're updating. The likelihood of survival changes because we know now that we're talking about a third class passenger. And so for that, we don't care about these first and second class passengers. We know that we're talking about third class passengers. So in that case, survived is 181 divided by, again, we're only curious about the third class passengers, so we divide by 709. That is something around 20. It's on here somewhere. Oh, it's not. I think it's something about 25.5%. You can double check my math. But definitely less. Okay, so you're in a worse chance. You're in a worse situation if you were a third class passenger. Okay, other things we can pull from this. So we can do kind of general probability. We can do a conditional probability. We can also do what is the probability of, let's say, second class. So what's the probability we found somebody that was second class and died? Okay. And in this case, what does that mean? That means, let's Venn diagram that real quick. So we need second class. We also need died. And what we're interested in is this overlap. Right? We need them to be both, to have both been a second class and have died. So how do we find that in our contingency table? Well, what does it mean to be both second class and have died in this table? Well, we need to have died and to have been second class. So that is this 158. So 158 fall in this window. Okay, and so what is that likelihood? That is 158 divided by the total number, right? So in this case, we are including all passengers because some of these passengers not in here are non-second class, but that counts in our calculation. And so that is something around, I think it's 12% basically. Okay, so we can find these additive or these overlapping, these joint probabilities. We can find that in the contingency table. We can also do things like, what's the probability that let's say we want second or died. Okay, probably not a super useful question in this scenario, right? I don't know how worried you are if they were second or died, but you could imagine other situations where we would want that or, okay? And so how would we go about that? So again, this is going to be the same Venn diagram, but this time we want all of the seconds to be counted and all of the dieds to be counted. But our biggest issue here is that we can't double count this. We need to make sure we don't double count that middle part. Okay, so if you recall, the probability becomes, we want to add up, so this is probability of second plus the probability died. But we do have to remember to subtract this off, subtract off the and. Right? If we don't, those people are going to get counted twice. So we subtract off the probability of second and died. Okay, again, all of that can be found in our table. So what's the probability of being a second class passenger? We had 277 out of 1309. Okay, what about died? We had 809 out of 1309. But we do have to then remember that there's this middle part that we've now counted. We've now counted these people twice, right? And we need to make sure they only get counted once. So how many people both were second and died? We had that here, but again, we can find it up here. It's that same 158. So 158 of the 1309 were both. And so we could this is the plus, we could change these all into percentages, or we can simply do 277 plus 809 minus 158. When you calculate this, it should be 70.9%. Yeah, so again, 70% were either second class or died. I don't know if that's that useful a question here, but these types of questions we can find, or these probabilities we can find in the contingency table, and so that can be quite helpful. Okay. So what I want to turn to, so now this is a lot of what's going on in Chapter 5. But the last part of Chapter 5, or the last quarter, third, we turn to a different kind of general concept, and that is how do we count things? Okay, sounds pretty basic, but as we turn to more complicated probabilities, the numbers are going to get quite large. And so it's going to be very helpful to have some quick formulas to be able to count up possibilities. Okay, so for instance, so it was quite easy for us to quickly crunch things like LeBron hitting 2 free throws or missing 2 or making 1 or the other. But if we start to expand that and say LeBron's going to shoot 14 free throws in this game because the refs are going to be whistle happy. If he's going to shoot 14 free throws, what are the odds that he makes 11 of them? Or what are the odds that he makes 2, then makes 2, then misses 4, and then makes another 6? Okay, so we can start to develop those types of questions, but the number of different possibilities. So for instance, what are the odds that he makes 8 out of 14? Some of those scenarios would be him making the first 8, then missing 6. Maybe he makes 7, misses 1, makes 1, misses 4, or however many are left. Okay, there's a whole host. He could miss 6 and then make 8. There's a lot of different possibilities. And so keeping track of all those possibilities is going to be important. And as we'll see, it's going to be almost impossible to write them all down. So we're going to develop some formulas to help us build the math around these types of questions. So while these formulas might seem a little kind of overkill as we learn them, they will come in quite handy in another chapter or so. So the question I think I have written down is how many different orders can you put the colors of the rainbow in? And I think what we're going to do, where am I? Okay. So we're going to think about red, orange, yellow, green, blue. We'll call it purple. There's probably debate about if I'm supposed to call that violet. So we have 6 colors. So what order could we write these in? Well, we could write them in red, orange, yellow, green, blue, purple. We could flip the last 2. We could flip the third. Oh, that's not. Okay, we could do blue, green, purple. We could switch purple, blue, green, right, and so on. We could then start with, what about orange, red, yellow, and so on, okay? So you can see quite quickly that this is going to get very expansive. And in fact, we'll be able to crunch here at the end how many different rows we would have if we did try to list them all out. So one way to think about this is in that first slot. I have a couple examples here that have different, right? But I could have yellow, green, blue, and so on, purple, red, orange. Okay, so that's another one. So in that first slot, I have how many options available to me? I have 6 options. Okay, so I have 6 options. That's hard to see. Okay, once I've chosen the first, whatever color is going to go first, I then have some options left for the second slot. And in fact, I have 5 colors left. Okay, in the third slot, I will have 4 options left. In the in the fourth slot, I will have 3. In the 5th slot, I will have 2. And in that last slot, I will have chosen 5 of the 6, and so I'll just have 1 left. Right, by the time I've listed the 5, I only have 1 left to go there. And so this is a way to quickly count up or multiply to the number of different ways I can write these numbers. Now, this is called a permutation. And what's important about that is that I care about the order, right? I'm asking about what order we can put these colors in. As we'll see, we will do a different formula if we just care about the combinations, okay? So it is important that these are different, just changing the order makes it different, okay? So the permutation formula is more complex than this, but we will turn to that in a moment. So another way to write this, 6 times 5 times 4 times 3 times 2 times 1, mathematically we can write that as 6 with an exclamation point, which is 6 factorial. Okay, and again, seems kind of not that important right now, but we'll turn to examples where trying to write out all of these numbers, say you're starting at, again, maybe a deck of cards where you have 52. We can't write out 52 times 51 times 50, blah, blah, blah. So we use things like factorial. Okay, and this simply means 6 times 5 times 4 all the way down to 1. Okay, so in our case right now, this is the answer. And so this becomes what? 30 times 4 is 120, 360, 720. So there, if we were to try to write out all the different orders here, we would have 720 different orders. Okay, again, so that's kind of interesting to note, but trust me that this is going to be helpful when we try to calculate percentages down the road. Now, the full permutation formula is NPR, where n is the number of objects. Here we have 6 objects. And r is the number we're selecting. So again, we've selected 6. So our case is 6p6, but the formula is n factorial over n minus r factorial. Okay, and so in our case that becomes 6 over 6 minus 6 factorial. Okay, and we'll see an example here in a moment what the difference is here. And in this case, so 6 factorial over, let me just make sure I'm on the screen. This becomes 0 factorial. Okay, 0 factorial, you might have to just kind of memorize this, but this is 1. 0 factorial is 1 mathematically, okay? Kind of just something you have to remember. And so this just becomes 6 factorial. So the number of permutations is 720. So why did we even care about this denominator? Well, we were in a special case where we were selecting all 6 options. Okay, so what if I really actually only wanted, I can't include all 6 colors. So let's say I just want to order 4 different colors. Okay, so what are my options if I want to just get this out of the way? I have 6 options, but I want, so I could do red, orange, yellow, green. I could do red, orange, yellow, blue, red, orange, yellow, purple, orange, red, purple, yellow. Okay, again, these are permutations, so these are different, even though they're the same 4 colors. Okay, now, again, as we can probably see quickly, this is going to be a long list. It's probably not going to be as long, but we can figure out exactly how long it would be. So in this case, we still have, so in the black case over here, we have n equals 6. We also have r equals 6, right? So r is the number of objects we're choosing. N is the number of objects that we have available. So we still have 6 available, but now r is equal to 4. So when we logicked through the number of order or the number of options here. We talked about in that first slot we have 6 choices. In the second slot we have 5, and so on. In the blue case, the first slot, we also still have 6 options. Right? We could pick any of the 6 to be our first color. In the second slot, we still have 5 options. In this third slot, we still have 4. And when we get to the last option, we still have, or the last slot, we still have 3 options, right? Because we've used up 3 of the colors. There's still 3 to choose from. What's changed is that we don't have this times 2 times 1. And so our answer is going to be 6 times 5 times 4 times 3. But we don't have a shorthand way to describe that mathematically. And again, as we turn to more complex scenarios, it's going to be helpful to be able to shorthand things. So how do we shorthand this? Well, this is 6 factorial divided by 2 times 1. Right? Because if I had 6 times 5 times 4 times 3 times 2 times 1, and I divide by times 2 times 1, let's just write that out. 6, 5, 4, 3, 2, 1, and divide by 2 and 1. These cancel out, and I get what I'm after. Okay? So let me start with 6 factorial on the top, and let me build 2 factorial on the bottom. What is 2 factorial? Well, if I put however many colors or options I have, and I subtract off how many I choose, I'm left with 2 factorial. Okay, so that is logically what we're trying to build here and how we get to that. So this permutation formula, that's what it's doing. It's telling you, okay, write out however many different permutations there would be if you selected all of the objects, and then take off the last few slots, or however many you don't pick. Okay. So hopefully that's helpful to help this sink in, is where it's coming from. So we're trying to build this concept of 6 times 5 times 4 times 3, and mathematically we can describe that as 6 factorial over, or n factorial over n minus r factorial. Okay, so that's just one of the equations, and again, it's going to matter. So a lot of this probability comes down to being very specific about what we're after. So here we cared about the order. Okay, and so that led us to the, I erased it, but that led us to the permutations. If we don't care about the order, we go to combinations. Okay, and again, what the combination formula is going to try to deal with, or what it deals with, is the fact that these are the same. Okay, red, orange, yellow, purple, orange, red, purple, yellow. Those are the same mixture of colors, right? So if you're putting them in a paint can, you don't actually care which order you spray the paint in, or the dye, or however paint's made. And so the combination formula is slightly different, but it takes into account the fact that those are the same. So the combination formula is almost the same. Okay, so I'm just going to write it up here. We won't walk all the way through the example, but it's, again, n factorial. We have the same n minus r factorial, but we add this extra r factorial into the equation. Okay, so the same logic is applying, and then we're making an adjustment, and this is going to account for all of these doubling ups. And so we can walk through an example of that on Friday, but just as a way to kind of try to put this all in a box and figure out where we're going with these different formulas. These are heavily related. Again, just like we have to make decisions, are we talking about independence or not? We have to talk about, do we care about the order or not? Okay, so on Friday, we'll walk through some more examples of this. I'll probably send out or post another set of some questions. We're also going to dig into what's called Bayesian or Bayes' rule, and we'll walk through some examples of that. Now, I'm going to warn you that Bayes' rule, Bayes' rule is confusing, and we're not good at it, especially the first few times we see it, and even when we're aware of it, as we'll talk about on Friday, we're not very good at it. So we'll walk through some examples, but I encourage you to dig into the material and try out maybe some of the examples from the book before we get to that, and I think that'll help our discussion have it sink in more. So so look for that on Friday, and I will send you an email in the next day or so giving you some more specifics about the exam coming up. But yeah, other than that, we'll see you on Zoom on Friday, or if you can't make it right at 11:30, then it'll be posted later in the day. And probably this version, but at least one of the versions of today's lecture will also be posted. So if you want to go back and see if you didn't catch everything I was doing, you can go back and look at that. So other than that, we'll talk to you soon. I'll stick on here for a couple minutes if people have questions. But yeah.